one thing I wanted to give appreciation to was three websites that have been very helpful for me going through this process. The first one being non-computer graphics using WebGL. Even though I'm not using WebGL, this is a very good resource for, figuring out, okay, how do you model things, how do you interpret things, and how should you think about making things. This is a very good website, webgl.brown.net. This is probably where I get most of my information from. The second one is Tiny Renderer, which is also quite great, and having them both as resources that flip back and forth between, seeing when they rhyme and when they don't, and different ways to go about it is quite nice. So Tiny Renderer, I think, is pure C++ CPU. This is more GPU focused. In this one, obviously, in the same way in Haskell that I've defined my shaders in a certain way, they've gone about defining their shaders in a different way as well. And the last one is this one, GPUfundamentals.org. And this one was very good for helping you figure out how to actually think about the fragment shader. So yeah, big shout out to these three websites, as they've been my biggest teachers on this entire journey. So this is a renderer built in Haskell, running purely on the CPU, and yeah, the goal is to figure out how to make this as fast as possible. The renderer can also support multiple objects within the scene. However, when this happens, performance falls off massively. I've got suspicions as to why, but we'll discuss those when we come to that. One thing that's also quite cool is that meshes can be textured or untextured, and depending on that, that can have impacts on how quick the renderer runs. But yeah, I'll come on to discussing why I think it's slow textured objects later on. First things first, let's take a quick look through what is this renderer's main function. We have a big function called canvas loop, and that is where we enter and function things. So in our case, we just set some variables, such as width and height of the viewports. I'm on a 1440p monitor, so that's going to take up a slightly less than a quarter than you'd see on a 1080p screen. That doesn't matter. Set the values for our view frustrum. So our near plane is going to be 10 units out, and our far plane is going to be 20 units out. The renderer is tiled depending on how large of the tiles you can either make it, so that way it's not tiled at all by just making it the big one with dimensions, or you can divide the screen into whatever size of subdivisions that you want at individual threads or independent threads to pick up what is there on the screen. We then generate some bins which correspond to the different tiles that are available. We initialize some buffers. So right now I've got position, albedo, or color. Sometimes I think it's diffuse buffer or albedo buffer or color buffer. They're all the same thing. And then the normal buffer. And the position buffer I also use for Z buffering as well. We've also got a canvas, which is where we're going to write all of our results to. And say, for example, if I change the background, any lighting calculations to take place. So that can be useful for debug if I just want to have something that is more easily visible. Cool. I also define a model that can be stored, that can be loaded from storage. I have to do it this way because the way that my parser works is that not only does it parse the OBJ files, it also needs to then do some stateful calculations on itself to then rewrite some values that it actually passes in from just the vertex data, and then sometimes you want to overwrite the text or the text or normal values that come with it as well. But with the OBJ models and probably then the mesh type model, we always say, okay, it can take in some kind of diffuse texture map, it can also take in some kind of normal texture map, and this one will be specular. And if we have it, then put it in there, and if we don't, we just leave it as nothing. And then this is just the modifications I use to then move all of the meshes back into the frustrum, so in our case at least -12, so that way all of their vertices are going to be inside this 10 to 20 region, and we're going to downscale it as well, because if we're using a, here's an octagon that I made. Yes, here's an octagon that I made, and then I convert it into a mesh, which I then load in laser, so this won't have any normal textures applied to it, but if I did have like some kind of normal texture mapping data, and I put that there, and then also added, so this is the index into the vertex that it is dealing with. So this one's going to be the texture map, the new one for the vertex, and this is going to be the normal map, which way the vertex facing. And then just say that I can load things in either as a textured mesh or just a plain mesh as well, which I'll probably show later on. Some values to initialize the window. See, I've defined some lights over here that we can play with. They're all kind of generally in the same area. The only difference is probably this one, which is just kind of like a backlight. So if I enable this one in my fragment shader, then you'll see that the spinning octahedron we had before the left side that was completely black, well now it's going to have some light coming to it from the back to the back and the left that should make it glow a bit orangey. Yes, so some of the colours absorb the blue, and so yeah, it's not that you always get a see, if I make this into a white light, then it should be a lot more obvious what's going on here. And now if I make that into a white light, it should be more obvious that I do have a lighting behind the model. You can see it's further into the view frustrum, and it's on the other side, so it should be towards the left. And there you go. We have a light from the, well, you can tell it's from the back because when this comes forward, it's not as lit as the front side. So yeah. We have this concept of shaders, which I want to talk about because they're quite interesting, and I want to show how they work. But the idea is that you can build like little functions that can either work at the vertex level, the prim level, aka groups of vertices that make a face, and the mesh level, which is groups of those parameters that are grouped together. And essentially, you don't have to split your shaders work in different parts. You just build an overall shader, and then once you have that, essentially you can have that work on any mesh. And one of the things I like to do is to decouple this from, at the moment, the shader gets put into, where does the shader get called? Yeah, so the shader gets called whenever we're filling our buffers. Ideally what I'd like to do is say put the shader probably somewhere in the mesh object, so whenever we call mesh objects, it should be something that should take in some kind of shader as a parameter, which is then called when we're filling the buffers, so that way we know what kind of effects you want to run on any mesh that we want. So that should be a relatively simple change, and that's something that I just came up with today. The big one is the render thread. So, on top of all the things that we've had before, aka just getting the models and defining some objects and shaders, the actual render thread function, which is what we're doing here, is we take our buffers, we make them mutable, then we work with those mutable buffers and pass them through and fill them with useful information. So here's a useful position buffer, color buffer, and normal buffer. In terms of fragment shaders, right now I just have them as functions that produce a color of a pixel, and we'll come on to that later when we look at shaders again. Once we've figured out what delta time is, and we rotate the model by 20 times whatever delta time is, we fill our buffers. Once the buffers are filled, we then freeze them. We then render all the tiles from the buffers using the fragment shaders. So the fragment shader is going to index into every single index into our buffers and color our output pixels in whatever we need to. Small things to then swap what's on screen, present it, and then we reset our buffers back into easy to use values. Just perform sculpture selections, that way we have green frame times. Without this, I get stutters every other frame, and so yeah, this is just helpful to have. And yeah, that's the core rendering thread. So let's click on build shader. In our case, vertex shaders are simple functions from uspace to uspace. From shader, then you want to be able to have them in some kind of container which you can map over. So Frontier you can fold down into one value if you want. So foldable, something you can traverse, go over the structure and change producing new structures, so traversable. And interestingly, I've got a monoid constraint here as well. And the only reason I have that is because sometimes it's quite useful to be able to say, okay, yeah, when I have a prim that is, not, it would be nice to be able to arbitrarily connect outputs of prim shaders together independent of order. And so having like some kind of neutral prim shader element would be very useful. And so monoid, when you combine the container and the view space vertex together, just proved to be very useful. And it was only useful in that one case when I was defining one shader, and I think that was the backface color shader, which I'll show later on. Alright, and then similar again, a mesh shader is, you already have your mappable instance. I mean, this could also be mappable as well, but it just helps out with traversal because, yeah, either way, I'm going to be traversing the structure and then mapping it into the vertices that are there to get more vertices out. So that works in my shape so far. That said, if I find more class constraints that are useful, I will probably just add them in. So then we have these like individual shaders, but then how do we combine all the effects together? And the key to that is to find a vertex processing shader, which is we have all the stages together bundled into one, and then the idea is that you start off with a shader that doesn't do anything, aka it just takes whatever it gets and produces the same thing, and then to combine them whenever you pass in shaders that do different things, take your vertex, run the first shader, run the second one, and so on and so forth, and do that for all of the things that are defined. So this is a prim shader that, this is a mesh shader that does backface cutting, but you don't do anything else to the other stages. That's fine because these are still going to be identity, and use build shader to then combine all of these. So we have a nice little combination function, and we just fold over that to then create like some kind of uber shader, which is very fun to invoke it. Before I was doing all kinds of arcane nonsense to get this to work, but actually it turns out that you can just get the functions out and use those functions. Cool. So what is a fragment shader? So at the moment, I don't really have a definition for a fragment shader other than we have a fragment shader output, which is going to be our packed canvas color. And we'll come on to packed representations and stuff later on. But yeah, at the moment, literally all it is just something that computes a pixel, the color of a pixel. Well, let's take a look at one shader, and one that I really like is random face color shader. And this was very useful for debugging early on. So the idea is that we define a function. In our case, it's going to work on the entire mesh. And the idea is, okay, we've got a color faces function, which, in order to figure out what we're going to take in our vertices that we have inside the mesh, and we're going to map map and accumulate this color generation function. And what this color generation function does is that it will give us a new generator. So probably taking some generation generator, we're going to make a new generator on every single step, and we're going to map all of the vertices in our face to be a new color. And yeah, and then that will just keep going on and on and on. Whenever we generate a new color, aka gen col, that's just going to give us some random colors within the range 0 to 255. Generate some new generators and then return us the newest generator of all of those, and that gives us that generator over there. And then we use this function generator color to then just say, okay, yeah, with the view space vertex that we just received, overwrite its color variable to be the color that we've just computed, and we're going to map that over every single vertex in the face. Let's take a look at it in action. So let's do this on our unslow, because I've got like two very high poly models and they're both hitting the color and vertex buffers pretty hard. They're going to be hitting all the buffers quite hard, and yeah, these should all just be put into one gbuffer. But that is something that I'm working on separately. So there you go. Yeah, as you can see, it's running quite slowly. But as you can see, with no lighting enabled, we can see that every vertex in the untextured model. So okay, it's not getting its color data overwritten by having a texture file there or a normal texture file there. All of those faces have been written to be a different color, and this is very helpful for debugging earlier on, as well as also modeling what the shader pipeline should be. And so yeah, that is such a function that you can use. As you can see, we're down at like 0.5 FPS. Like this is tough to run with the current setup. So that is shaders, more or less, and you can see some more, and you'll see some of those when you'll see them in the repo, and it'll be nice to just like build like a good little list of these. Yeah, most of these were just built for debugging, seeing whether or not the things I was building were building correctly. Back-based color shader, you can imagine it's a nice optimization trick to make sure that we don't render vertices are not facing the camera. And also as well, I can make a front-faced color shader, which is probably going to be very useful when I'm doing shadow mapping later on. I just got to figure out, okay, am I shadow mapping in the Vertex shader or the Fragment shader? And spoiler alert, that is quite difficult to figure out right now, but we'll work on that another time. So yeah, a quick one is also about a fragment shaders, because we haven't really done that, and you'll be interested in that when I clicked on UX fragment shader, it took me to light.hs and not shader.hs, and that's just how this fell out. Essentially, the idea is that it was just easier to write the fragment shaders in this position. So I've defined some different light types. Area lights I haven't done yet, but I've definitely done point sun spotlights. And the idea is that, like I said, calculating a pixel's color is depending on the amount of information that you have to give it, to be quite honest with you. And even though, I think in all cases, these take an index into the buffer, do they? No, they don't even do that. So yeah, these don't even take an index into the buffer themselves. They are more interested in saying, okay, do I have the information I need to calculate what color this pixel should be? Do some calculations. And once we've done it, we get an updated color. Once we have that updated color, we're going to put that into our result and then just return that result. And I'll talk about this poke and plug interface later on. But yeah, that's just a little bit about the fragment shaders, how they work so far. And then yeah, utilize fragment shader. This is where we start to actually look into the index, into our buffers, which is what gets us our original colors, which allows us to then pass those into our fragment shaders to then figure out, okay, what color should they be. Okay, so shading was nice and all, but how do I actually get stuff into the buffers? And this is where this fill buffers function is very useful. So before, it didn't actually see the shape. I used to have just like a function called obj fill buffers, because it's only works with obj so far. However, I've now made like a general mesh function, which I can use to define meshes of different object types. So my hope is that like I can make a USD-based scene viewer, as well as I'll be able to import files of different both texture formats. The thing that you, the user, are using doesn't really matter, but you have access to all of these. Yeah, meshes for buffers takes a list of meshes that you want to display into the scene. And yeah, the tile size took earlier, the bins we generated. This is a bit of a legacy. This probably could get folded into the mesh data itself entirely separately. The projection matrices that we're using, aka which projections we're using, and we'll come on to projections later on when we show projection. The camera projection, dimensions, the width and height of the viewport, the shader that we define, which again probably could be folded into the mesh. Thickness, which is a legacy holdover of trying to make fully bound triangles in the buffers we had earlier. So let's take a look at meshes for buffers. As you can imagine, first thing we're probably going to do is we're going to fault map over all of the meshes that we have using some other function that will fill our buffers. So let's take a look at mesh for buffers that works on one mesh. In my case, it's actually quite nice because it simplified what meshes were a lot in that. Right now I've just got two types of my mesh class, which we're going to look at right now. So in my case, a mesh can either be a base mesh, which is just a mesh info, which we can see, we have the name of the mesh, its transforms and vertices, and some indices for the faces, so that way we know which vertices belong to which faces. And the vertices themselves also have quite a lot of information, such as they'll have position, a color, some normal, and some texture mapping data. This means I can reuse the mesh info and then just say, yeah, I have some texture, I have some normal texture, and I have some specular texture as well. Yeah, once we have that, we have our rasterize functions. In our case, let's take a look at rasterize texture functions. Texture fragments and rasterize fragments more or less do the same thing, as you can see. So the idea is that we're going to generate bins, aka the data for where every vertex is going. And then once we have that view space mapping, this is going to generate the areas where each vertex lives. And you can imagine that our vertices take a space in screen space. If we divide the screen into tiles, then we can make sure the vertices within that tile then get rasterized, so that way we're not having to work on the whole screen at once. But yeah, once we have new bins, we're then going to map over it. The first mapping that we're going to do is to say, given the list of vertices that we have for every vertex in that, so we're doing this concurrently for every list of vertices that we have in that, rasterize the textured fragment. So what does that look like? Well, we have a list of vertices, we have some function that is going to unfold is say, if I have at least 3 vertices, I can make a face from it. And so generate the fragments that are inside this triangle using our thickness arc projection. And then once we have those fragments, we can then rasterize them with the texture. And then we just drop one from the top of it. So say for example, this is a quad, or render is a bunch of triangles in order, raster texture. So what do? We do a nice early Z update to say for the inputs we generate gen fragments, which reminds me I need to look at gen fragments. So what gen fragments do? It does a lot of stuff. The idea is that if you have some vertices, and the idea is that you do a bunch of transformations to then say, let's make some data that we can use to render the screen. So first and foremost, what index into our buffer will this pixel or fragment result onto? It will have some templates position, some templates color, normal, and texture coordinate, depending on where it is. Because gen fragments is a list comprehension that's it's a big list of vertices that we use. And you can see that when we then get those fragments, so these ones here, raster texture, we then say, okay, for every index into a buffer, the new vertex information that we have and the time space matrix. We don't do any work if the position in our Z buffer is newer. Yeah, if our position in our current area is greater, so I'm working on a -1 is the closest. No, I've got 1 is the closest to -1 is the furthest in my clip space. So larger values are towards the front and really far away values towards the back. So yeah, if we have something that's newer, then we actually do some work, otherwise don't do anything. And if that's the case, if we are going to do something, then actually do some work. If we don't have it, then we just use the vertex's normal and color information. If we do have a texture, then we're going to use it from the actual texture itself. And let's take a look at right color from textures. So it's very much going to be right normal bar from texture. If we have some texture data, in our case, diffuse texture data, a data type. In our case, I'm just interested in diffuse TJ files. I want to also do procedural maps, which is probably some other branch I'm going to work on. And yeah, obviously, TIFF, PNG, that's going to be something that could be added to this, the rest, which is sample into our texture. And then once we have the color that we're interested in, we then just write that into our color buffer. And so on and so forth, nice and simple. And once we fill our buffers, the next thing to do is to render all the tiles, and this is where fragment shader comes into it. So render all the tiles, we have our tiles, we're obviously going to do that concurrently. And then the tiles is figuring out the bounds of the tile, and then for every XY position inside that tile, get the index, run the fragment shader on it, and that fragment shader is going to, in our case, it takes the index into the buffer and just calculates what it needs to do. Once we have a color, we then just write that into our canvas. Once we're done rendering our canvas, we then freeze that and return out here. Once our canvas is returned, sort of texture, yada yada yada, present it to the renderer, and that's how we get the new frames every single time. So yeah, you probably already see like there's a massive inefficiency here, and that we are working with 3 separate buffers. This should probably be one big G buffer, and that's something that I'm probably going to work on later on. The next thing I'd like to talk about are these functions: poke, update, and pack, which you might have seen floating around the code base. You might have seen that we have these fields. So the idea is that we can define some types of fields that tell us how wide each individual packed representation of some structure should be. So say, for example, if I only need 3 bits for a channel, I could say, okay, yeah, this field is now 3 bits wide, this next one is now 4 bits wide, this one is now 6 bits wide, and then we need 13 bits in total. This entire thing fits into a Vertex scheme, and then I have like a nice type-safe interface into poking and plucking values from there. So that way I don't have to do the calculations and shifts. I can just literally do it from some type level representation. Doesn't calculate ahead of time for me. And so that's what this big interface is for. We use type family to calculate how wide our containers should be up until 64 bits. So I think that the biggest that we can have is 64. Derive some instances, and then in order to figure out, okay, how do we know how big everything is, we use this bit structure type, which we then use in a bunch of type classes later on. So nice little menu constraint. We can also calculate the max bound that can be time structures. So, and yeah, that gives us the maximum value that we can fit into the structure. And this is helpful because whenever we want to, say, shift a normalized value between 0 and 1, we can then just multiply by the max bound, and that will give us what we are working with. Same again, if we want to normalize values, we can get this max bound and divide by that to then normalize it, which is quite helpful. So yeah, a bit on unpack and unpack. The idea is that we can take some type of list of fields, and if we put them next to some kind of bit structure, we can then get a packed representation of it. And the best part about it is because it's got no new constraint, I can pass on this as knowing like how much space this takes, which is massively helpful. And then obviously, if we could pack it, then we could probably be able to unpack it. We obviously have a bunch of functions to help us do that at the type level, and then just a bit of extras down. But actually, the one that's like really interesting is the generic interface, because one of the things I really want to be able to do is do stuff like this, where I could say, okay, well, given some data type that I know, 11 bits for the red channel, 11 bits for the green channel, 10 bits for the blue channel, is there a way that I can generically derive the pack and unpack functions? And I'm not been able to use it using pack and unpack, and I haven't been able to do it using pack prime and unpack prime. And yeah, that is the generic interface. It just involves a lot more type level programming to work with the type level lists, and those were the biggest problems, especially type level lists whenever we are building the structures. Yeah, it was not the difficulty, it was breaking them apart, and that was the first and only time I ever used unsafe coerce ever. But generally the idea is that, well, I just need to convince GHC that these two things were the same essentially, and that I would have just had no way of telling GHC that append to list B was the exact same as to list of A, essentially, was my understanding of this at the time. Very similar down here, we also have an unsafe coerce, because again, we're trying to say that, okay, if we're going from struct, and this is similar structure, we want to start from, we have a representation of A, and some empty lists we're starting with, and essentially appending these two together is the exact same as making the entire list. Similar in the same way, it's exactly the same way as if you had 1, 2, 3, and then you want to plus plus, you still have 1, 2, 3. So it's kind of convincing JC that these are the same things. What is nice though is that I've been able to use this pattern all throughout the stuff I'm working on, which is massively helpful. So for canvas colors actually, because these get packed all the time. So yeah. I'm just working with the standard RGB AAA setup, and so being able to say, okay, when I'm building a value and make it a packed canvas color, this is great because similarly as well, SDL's window is also working with RGB AAAs, and this is wonderful for me because I can literally just take the values that I've packed into my packed canvas colors and then just put those into literally swap the pointers to the arrays in a swap canvas, and all of the information lines up. And this is great because so long as I know what my destination type is, aka this RGB AAA, I have a nice easy way of coercing from one value which I can unpack and then packing that into a new structure later on. So even if the bit widths are different, once I unpack it and I have some value and then want to pack it in again as some other value into some other structure, I have the ability to do that, which is quite nice. And that's one reason I really like this API and I really like the structure. Another thing I'd like to talk about is projections and how all of those work. So yeah, this is probably one of my favorite modules in the entire thing, just because of how neat and easy it is, and how I think it shows like some of the best things. The first thing I have is I have some data type that represents some projection mode, and then I use data kinds. I think it's data kinds to then say, okay, I'm going to create some type called projection. It's just a 4x4 matrix. But I can say, what kind of projection it is, and make that type safe whenever I want using this data kind. So we often see in code that I have, projection perspective or projection orthographic, and depending on, the kind of projections that I make, this is very useful because later on when I'm going to be doing shadow mapping and lights, for some lights like sunlight, it makes sense to do it as a orthographic map, an orthographic projection, and then I can constrain that type and say, okay, yeah, I need to project this in an orthographic way. Or most of the times I'm working with the perspective projection, and other times when I don't really care, I can just put some projection A in there, and or some projection lowercase type variable, and then it doesn't matter so long as I just have some 4x4 matrix that represents a projection. And another thing I like about this module is that it helps me keep track of which stages the vertices are. So if you remember shader, I make my vertices specifically work on view space shaders, and so it's easy for me to figure out, okay, what is it that I'm doing with the shader at this point. And actually, a lot of the vertex shaders that you look at on the internet tend to do that as well. They just tend to transform vertices. What's helpful is that I can take the vertex into different stages, and it's literally just new type wrappers around different things. I can also put wrappers around the transform themselves. So all of these are just in 4x4 matrices, but because they're new type wrappers around what they are, I can make sure the correct matrix gets applied at the right time, in the right order. But yeah, this has been a very fun project. I really like it. And I hope that one day this is going to be quite fast and does a bunch of cool stuff. All on the CPU, again, it's nice, and it's all well and good to make a fast render of the GPU. However, one thing I'd love to be able to do is be able to define my vertex shaders in just like pure Haskell, and then just use the language that Haskell's given me to have a rich way of doing it, and just define shaders in any language, and just push that information into the GPU whenever the GPU needs it. So yeah, this is a quick rundown. I'm sorry this is very scatterbrained and not very great. But yeah, if you have any questions, let me know. My contact details are in the description of the video, and also in the discourse and Reddit threads and so on and so forth. And yeah, there's a copy of this repo available on GitHub now, or at least it should be by the time this video goes out. So if you want to fork this and work with it, go ahead. I'm not going to work with it since I don't really want this on GitHub, at least as I develop it. But I'd rather put this version out here. Hopefully someone here can work with it and learn from it. And yeah, if anyone finds it interesting, go ahead, have some fun, and yeah, have a great day.